1. All right, this is Juan Carlos. My Panther ID is 6229898.
This is Jose Portillo. My Panther ID is 5869027.
And this is Anthony Diaz, Panther ID 2890516. And this is the final design project. And the design project is called Power Source Gauge. Now, the main objective of this design was we wanted to create a device that can not only sense current voltages levels of a source, but also display it in a certain way. Now, normally tools to make this development process or fast and reliable are not always easy to access, and they don't always come at a low cost. So that was the main reason why we wanted to do this, was because we wanted to create something a little simpler and a little more straightforward. Now, new application vendors will always have a market for this. And we wanted to design a device that can not only read the voltages, but display using lights. That's how we wanted to display it, not just numerically. Well, you know, the lights mainly were because it's a little bit more amusing and less boring way to show it than just the levels. The intention is to use the capabilities that operational amplifiers can offer when working as amplifiers and buffers together. The lights can be color-coded, that can range from yellow to red to green. And when we started building it, we wanted to have red to be the lower voltages starting at 0 volts, and greens to be rated as close to the value source battery. Now, we did find quite a few different projects online that were achieved similar goals to what we were looking for. The first project we found, he created an external circuit to their multimeter so they can read voltages from a circuit without inducing the current from the multimeter to a load. We did find the second project where this person created a multimeter using copper wire loops and created the loop to read the voltages. And then finally, there was a third that used Zener diodes along with the capacitor. Now, this third one was more what we wanted to reflect in our project, but instead of using diodes, they were going to be using amplifiers instead. And as you can see in our chart, we wanted to do something very similar to what they had. And after some research, we did find that our devices were reliable as possible, and we'd have to design it in a way that accepts different voltages levels. We also wanted to use all the analog devices only to test our understanding of the material seen in the class. And we wanted to avoid as much possible the use of controllers, such as Arduino. We wanted to do it ourselves. Now, we did have in mind to use a self-contained, meaning we didn't want to use any external power sources, and would automatically work when the source is connected. So once we got started, one of the first things we did is start analyzing the costs. Now, we didn't want it to go over $40, and we did anticipate that we needed to have some operational amplifiers, resistors, diodes, and quite possibly a few capacitors. Now, we will solder the components to a PCB and insert it into the enclosure so it looks a little bit more professional. It was more of a look thing. So initially, we wanted to design a device that can read voltages up to 12 volts. Now, we did run into problems with that. So the way our device was is that lights will light up all the way until it reads the voltage that it gets. Now, the lights beginning from the bottom to the top, they would stay lit until it got to the reading. But what we found when we went all the way up to 12 volts is that the initial lights would start going off one by one. It would still give us a reading, but the beginning lights would not stay on. So to go work around this, instead of going all the way to 12 volts, we started all the way to 14. We started from 0 to 4 volts only. And then we found all the lights would stay on until it read what the voltage was. Now, the way we built it is that we had our device enclosed in a plastic bin to cover the circuitry, and the holes are made on the enclosure for it to lead the lines pattern to show voltage levels. So as we started beginning this project, we made a schedule. And from March 9th to March 13th, the first part was to order the parts. Find out all the parts that we were going to need for this project and have them delivered and ordered. From March 16th to March 20th, we were going to have to design the circuit on the digital simulation. Make sure it was working there exactly how we wanted it before we started actually building it. From the 23rd to the 27th, that's when we actually started building the circuit and replicated exactly how it was on the simulation onto the breadboard. from March 30th to April 3rd, we started working the troubleshoot. And that's where we found out that problem with the 12 volts down to the 4 volts. From April 6th to April 10th, we moved the circuit straight to the PCV. And then from the 13th to the 17th, that's when we started to install all the enclosures and all the modifications, make sure, and then we started testing again to make sure it worked. And then that's where we got to where we are today.
Okay, so right now let me show you the circuit. One, you disabled screen
Got it.
sharing. Okay. Let me show you the circuit now. Okay, so right here, this is the circuit that we made for our project. As you can see, we have a battery source right here of 4.5 volts connected to ground. Right here, you can see in this part, this is where the LED lights would be connected. We have 2 resistors here, and then we have the device in the center. Okay, so in the device in the center right here, which is an LM3914, we have about 18 different pins. For pins 1, 10 through 18, this is where all the diodes, all the LEDs are connected to, and you input it. For pin 3, the voltage is provided to the device. Pin 4 is connected to ground, which is right here, as well as pin 2. Pin 6 and pin 7 are both short-circuited. Pin 5 is a pin that provides the input signal to the device. And then pin 8, in which we have a voltage divider right here connected to it, which will provide current to the device. And another interesting thing about pin 9 is that for pin 9, depending on like the voltage, you can light one specific LED at a time, depending on the voltage is provided to it. So for each of the LEDs to be light on, you need an increment of about 0.45 volts for each. So each 0.45 volts incremented will light an extra LED light. So let me show you the next image. Give me 1 second. I just need to, whoops. There we go. This is the block diagram right here of the LM3914 device that we are using. And right here, we have a bunch of comparators, op amps, which is something we studied in around lab 3 of this course. So we have comparator op amps here, which they're meant to compare the voltages that are being inputted into them. So in this case, where for each different light to light up, you need a certain amount of voltage, which will be 0.45 increments. So for this case, if we have a certain input voltage of, let's say, 4.5 volts, which is the rated battery, the comparator voltage will be comparing it with each other. And since it's 4.5, you'll have pretty much all of them light up in this case. And then for other voltages, like let's say 0.45 volts, only the first one would be light up due to the differences in the voltages being compared for each of the comparator op amps. And this is reflected right here for pins 1, 10 through 18 right here, as shown here in this diagram, which goes in conjunction with our calculations we made and the table and the testing we've done for this circuit, which you can see here. So this little thing right here, this device, the LM3914, this is the actual circuit right here for it, which was shown earlier. And that's how each light is turned on due to the comparator op amps here. Okay.
All right.
Let me just
So
share screen.
yeah.
Okay. Stop share. Okay, continue.
Okay, that's fine. All right, so now I'm going to explain how we started making the physical device from scratch, from zero, based on the design that Jose just showed. So we started with the breadboarding. Right here we have it. It's the same circuit as Jose showed that we designed on Portillo. That's the software we use. So the challenging part about this circuit is that we're not used to using an IC that uses negative feedback. That's not usual. We always use an IC that sends out positive feedback. So that was the challenging part here because we're connecting at first the LEDs on the opposite side. But the positive leg of the LED will be connected to the signals of the coming out of the IC. That will of course make nothing because, like I mentioned, the IC uses negative feedback. So we actually needed to flip all the LEDs, use the negative, the negative leg connected to the pins of the IC to be able to drive the LEDs. So here we see both of the columns on both sides. The positive ones, they're connected. They're shorted there with the wire on top. You can really see it. And then the LEDs. The IC is facing up, so we can see pin 1 is the first light, and then all the way here on the bottom is the second LED, the red ones, blue ones, and greens. So like Jose mentioned, every LED will turn on every 0.45 volts. So the first LED that will turn on for 0.45 is this pin 1, then pin 2, pin 3, and so on. We have the resistor here. We didn't have a single resistor that had the whole value that we needed, so we used 2 in series. This is the other wire going to number 8. And then the second resistor going to ground. So after we built the proto board, we had some issues. We tried to swap in the proto board, for different ones, trying to recreate the same circuit on different boards. On some boards it would work, on some boards it wouldn't work. We're really not sure why, so we decided to just go ahead and make it work on the actual prototype board. So this is the same design as before. We apologize for the soldering here, but the soldering iron that we have is not the expensive one, so it's not very good. But this is the same chip again. This is facing up. This is pin 1, and then this is the second LED, third LED, fourth LED, and so on. We have the 2 resistors here and everything else. So the wires for the ground, for the positive signal, and so on. So the intention here was to solder everything here in this little board to be able to put it in this case. I'll be showing the actual physical finished prototype so you guys can see why we use this little board. Here we have this green entrance here. This is for the voltage. This is just a way to test. This is a test point. This is the negative and the positive coming out from the battery. So this is just a way to test the circuit without actually being soldering anything to the board. So I had this test point there. And we use just the regular proto board wires. This is the other side. This is where we connect the 4.5 volts. We have this here, the negative terminal going into the circuit and the positive terminal going into the circuit. No, I apologize. This is the positive and this is the negative. Yeah, they're color coded to avoid confusion. So I use hot silicone in the back of the housing just to put it there to make all the device all together. This is another view from the side of the circuit. This is the back and this is the front. You see a lot of wires. There was a lot of cramping the cables when I closed enclosures. So let me show you the next one here. Since I needed to make holes, we needed to make holes into the housing to be able to fit the LEDs. We did that with the soldering iron. We added this sticker. We had it laid around to make it look better. This is just for looks sticker, so we didn't really see the holes into the plastic. Yeah, that's another picture. And this is how it looks in the inside. Yes. These wires here on top that look like a bus. This is the positive signal, and the ones in the back, these are the negative signals. Notice that the negative ones go to the IC, and the positive ones go straight to the signal, to the voltage. All right, so this is a portable charger. I tested before connecting it here. It was a 4.5 volt charge battery, so you can see all the lights turn on. Notice here the two zip ties. We know they look pretty ugly. That's something that we could make better later. But since all the wires were cramped inside and the housing was pretty small, we needed to use something to hold it together, and hot silicone wouldn't do it. So this is what, yeah, this is when we connect to the device at 4.5 volts. You see all the lights turn on. That means that it's full charge. And then on the this one, what is it? This is another view of the thing. Here I connected it to what? This is a 9 volt battery, but it was discharged. It had way less voltage than it was supposed to. So we connected it to the device, and it only showed 1.32 volts, as we can see, 1.35 volts, as we can see on the lights. So I'm gonna show the physical thing. So you can see it. This is the physical product. This is like showing the pictures. We have everything there. This is just so I can connect to the batteries. I don't have the exact batteries, but we didn't find any batteries right now at the market, so we're just using some batteries, the same ones that we use on the pictures. So I'll be showing how it works. But this is the same discharge battery that I show you guys on the pictures. So this is the negative. This is the positive. So you see, only 1.35 volts into this battery. So if I was to connect the other one that I showed there on the pictures. We see all the lights going on. So that means that it's fully charged. 4.5 volts going into it. So considering a few things that we need to change to this circuit, because as you can see on the proposal, we used 0 to 12 volts. And here we're only using from 0 to 4.5 volts. So some modifications needed to be done to the actual circuit. I'll show you. So when we had it like this set up, but with a 12 volt, all the lights, like Anthony mentioned, they will be on, but then they will start, if the voltage here surpasses the 12 volts a little bit, maybe by 0.3 volts or even 0.2 volts, the first couple of lights, they will start to go off. So that wouldn't work. That's why we went down from 0 to 4.5 volts. But some things that can be added just as an improvement to the circuit is here where the battery goes, adding a capacitor. By adding a capacitor, when there is any shortage or anything that works wrong with the circuit, the IC wouldn't be compromised. It would be fine. The voltage extra or the signal that is not supposed to go in here will go straight to the capacitor, and then it goes to ground. So that will it's kind of like a safe precaution for the circuit, so we don't destroy the circuit. And another thing that we could add is a diode, maybe a center diode points towards the LED. So even though this is a battery, it needs some type of protection so the current doesn't come back up. So that's another thing that we could do. And of course, we can make the circuit, maybe changing these two resistors here to make it more capable to read up to 35 volts. This IC can simulate this circuit, the same circuit, for up to 35 volts. So it'd be nice to simulate this, having the same exact device for more readings, so we can even add more lights. So we can cascade two of these two ICs, and then having 12 lights, 12, no, 20 lights to display voltage of a battery. So that's one thing. And another thing that we could improve for the future design is, the actual housing. We could 3D print a bigger one, maybe using less wires, so we don't have these zip ties wrapping around. They don't look very good. Yeah, that's it. All right, so that was our final project for Electronics 2. Thank you for your time.
Bye-bye.